recorder going too. So can anyone not hear me today? Okay, I'm not seeing anybody, so guess we're all right. Anything anybody wants to say before we get going here? Don't know what's going on in your life, but some folks are having some real challenges right now. Probably everybody. Well, I'll just say I hope that your family and friends are safe and well. I know if as many people as we have in classes, you know, the chances are pretty high that someone's having a real tough time. Anybody got a question about the class? Anything like that? Yes, Amira, what's up? You can type it or say it, whichever you want to do. Don't know what that was. Oh, wait a minute. Let's try this. It is on whatever was on the calendar. Let me see here. Okay, you guys' final is on. Okay, you guys' final is on Monday at 10 o'clock instead of 9 o'clock. So that won't get to sleep an hour. Anyway, it's Monday at 10 o'clock. Yep, that's right. Monday at 10. Okay. For some reason, the total put in the grade already, even though it's due on May 5th. Yeah, it starts putting in the grade when you start working on it, but then it updates it until the due date. So it should change, but that can be alarming when you first see it. But when you first start working on something in Sapling, then sometime along the way, the scores get transferred from Sapling into Blackboard, and then it'll be saying, you know, your grade is this, but that can change, you know, whatever you get done by the due date. So, and especially with the topic introduction, since they're 0 or 100. But if you see that it's done it wrong for you, please let me know. Anybody else got a question or comment or something? Okay, let's take a look at Blackboard. So I'll share my screen. I went through and got the recordings up to date, but I know I am probably not up to date on grading lab reports, so I'll have to get onto that. But first thing I'll be doing is getting this exam together. So we have an exam this Wednesday at well, normal time, 9 o'clock. It's going to cover chapters 14, 15, and 16. So that'll be on Wednesday. Okay. And like I've said before, now we have our guy at Sapling that will help us if we have some issues getting logged in. So the moment you notice that you can't log in, please let me know, and I will put you in contact with him, and he will do a Zoom call and get you going. So anyhow, that's my two things there. And talking about sapling, here's the remaining assignments, I think. Yeah. So the homework for chapter 21 is due on the 4th. So is the homework for chapter 19. The topic introductions for 17, I don't know why 17 is out there, but anyway, 17 and 21 are on the 5th and the 6th. Let me see if there's anything that you can still be working on. Okay, since the homework for chapter 16 was due on the 2nd, and you get 5 more days to work on it, then let's see, that would be May 7th. You could still be working on it. Of course, there's going to be a point deduction on it if that's your situation. And that same thing goes for the electrochemistry chapter. If you did not get it finished, you can still be working on it up through the 7th. And that's it on the sapling. So I'm going to stop sharing my screen. Anybody got a question now or comment on any of that stuff? Okay, in that case, according to what I have, we did not finish the worksheet for the nuclear chemistry chapter. That we did questions 1 through 3, and that was it. So I think what I need to do then is put you back in the groups, and then we'll go through the rest of the questions, starting on question 4. So what I'm talking about is this worksheet here. So according to what I have, we did those questions right there, but we did not do anything beyond that. Has anybody got anything different than that? Okay, so I'll put you back in groups so you guys can talk about your answers, and then we'll just put, you guys will put your answers into chat, and I'll just randomly call on groups. Okay, so got a few people that came in a little bit later, so I need to so I'll need to get you guys in your groups. Okay, got everybody in what I think is their groups. So I'll start this up. If you see I got you in the wrong group, send me a chat. I'll move you over. If you have a question, you can do the same. But we'll be getting going on this pretty quick.
It's just mad funny.
That's yeah. Okay, we made it through that thing. Anyway, I'll make sure the key is up for you guys to look at because you will be needing it. Um, anyway, we got a little bit more of this chapter. We ought to be able to finish it here. So I'm going to put the PowerPoint back up for it. So here we go. And looks like somebody's breathing heavy in their microphone. Okay. We stopped on slide 12, looks like. And that was one of those really messed up ones. Okay, I got rid of the breathing. Uh, anyway, uh, okay, so we did these 4 or 5 slides actually from the version of the PowerPoint that's in Blackboard because it's messed up here. So anyway, next slide is this, and what this one's about, it's showing how you can start out with like an isotope like uranium-238, and you can go through a whole series of decays. And they're representing the alpha decays with a green arrow, beta decays with a red arrow, and they're showing how you start with uranium-238, you go to thorium-234, you then have a, a couple of beta decays, you're back to uranium, but now the mass number has gone from 238 to 234. So we're dropping mass with really all of those processes. And that's what these decays are about, is to lower the mass so that we can get to a stable isotope. So anyway, I'm not going to go through all those, but eventually you wind up with an isotope of lead. So lead 206. So that's the way these decay series typically operate. Um, you're not memorizing anything or anything like that. I just want you guys to see this. So let's look at another slide unless somebody's got a question. Okay. So that gets us to the idea of a half-life, because when we have an isotope that's decaying, we can plot that as the amount of an isotope that's remaining versus how much time has evolved in terms of half-lives. So for this isotope, we've got cobalt 60, mass number 60. And when we start out, we have 10 grams, which, is 100% of our sample. We come back after one half-life, which is 5.27 years, and now we've gone from 10 to 5 grams. Then the next half-life is when we lose it's when we are half of 5. So half of 5 is 2.5. The time is now 10.54 from time 0. But what has happened is we've gone another 5.27 years from our first half-life. And then this last one here, half of 2.5 is 1.25. And our time period is 15.81 years from time 0. But again, that interval is 5.27. So all of these half-lives are all going to be the same number of years, 5.27. So then what we can do with this kind of stuff is, let's see, you could have a chart of data like, oops, I marked away, the mass remaining versus the time, and the question could be as simple as, what is the duration of a half-life? And then you would say, like I have down here, a half-life is 5.27 years. Now that's one sort of question. It could be that they tell you the half-life is 5.27 years, and they tell you how much you have in your sample to start, and the question might be, how much do you have after 3 years? Or excuse me, after 3 half-lives, I'm sorry, after 3 half-lives. So we know that for each half-life, it's going to decrease by half. There is a mathematical way to get right to it, but you can just write the numbers out. So 1 half-life, you have 5. Second half-life, you have 2.5. Third half-life, you have 1.25. So then your answer is going to be the 1.25 grams. Now there's some other more difficult questions that are possible, but I'm not going to ask those. Okay, I don't think it's appropriate for Gen Chem. So anyway, so that's the idea of half-life. Now we're going to see here in just a moment an application of half-life that you've heard before. That's carbon dating. And the idea here is you can have living organisms like an animal or a plant, and while they're still experiencing metabolism, they're going to have a certain ratio of carbon-14 and carbon-12. The carbon-12 is the dominant isotope. It's most frequently occurring. Like you can see above here, it's 99% of what should be there, with only 1% of carbon-13 and then a trace amount of carbon-14. So very small amount. But at the point where these organisms die, or to say become some sort of an artifact. So the cow winds up being, I don't know, a Native American, a native somewhere's leather jacket, or the tree becomes a, I don't know, a wooden box of some sort, something like that. And then these relics are found, and they're wanting to know how old they are. They can sample the amount of carbon-14 and carbon-12, and they'll see that the ratio is different than what would have been present when the cow or the tree were still living. And by the amount that ratio has changed, they can then calculate how many years have gone by. So as time goes on, you got less carbon-14, more carbon-12. And processing the samples is pretty easy, really, in that you just put them into a mass spectrometer, and it's going to give you the number of molecules that are carbon-14 and the number that are carbon-12. So you would do this with just a mass spectrometer. Okay, and that would give you your data that you could then look at to see what is the ratio of carbon-14 and carbon-12. Okay? Anybody got a question there? Okay, so if someone wants to, disagree with the estimated how long ago a particular relic existed, it's kind of hard to argue with it because these decay processes are continuous and they are the same. So it really is whatever the numbers come out to be. Okay, let's go on from here. And we're now going to get into application of some of this nuclear chemistry and in the production of energy. And this can be a good thing or a bad thing. We can do this, make electricity. If we were doing things properly, we would have a safe reactor and we would dispose of our waste safely, and then we would have the advantage that we're not increasing carbon emissions, and it would be a good thing. Now, the only problem is people don't do things the right way sometimes, and there's accidents, such as what happened in Chernobyl in Russia, where they were doing some testing on the reactor, and the proper people were not present, and they just let it get away from them, and the reactor exploded and spread radioactive material over quite an area. And probably saw in the news recently there are wildfires in the Chernobyl area, and that's causing some of this radioactive material to get pushed up into the air, and so it's then being distributed in the area. I don't know how far it's traveling, but we got one more thing besides those killer wasps that are coming in from Japan, and bad viruses and zombies. Anyway, but if we did things right, this would be a reasonable way to produce energy. It's not like Russia's the only one that screwed up. We've had some accidents here. They haven't gone quite as bad, but we've had people melt the core in a reactor and they have to shut that reactor down. In Japan, there was a tsunami that caused a tidal wave that flooded their reactor, and the big problem was it shut down their electrical supply, and they could not control the reactor. So they had not a huge explosion, but they did lose that reactor. So stuff like that happens. But if we're more careful about what we're doing, it is a reasonable way to produce energy. Now, the other way, of course, this is used is in nuclear bombs when we want to, really blow up a lot of people. Anyhow, I guess we've done enough of killer wasp and stuff on that kind of idea. So, but anyway, here's how it works. You start out with a neutron, and you bombard a radioactive isotope with that neutron. And the neutron becomes more unstable than it was before, and it wants to split. And when it splits, it's going to make what's called daughter isotopes. It doesn't always produce the same ones. There's some probabilities involved as to what you actually will get. But anyway, it'll split. And there's some energy right here, as you can see. But the biggest part of this, the most important one, is that it makes 3 more neutrons. If it just produced the energy and we didn't get the neutrons, this wouldn't be very useful, because while that's quite a bit of energy, we're only talking about one isotope ending up doing this. So that's not going to produce a lot of energy. But if we can have a situation like this, where you produce the 3 neutrons, and they then interact with these 3 isotopes that go on to make 2 or 3 neutrons, depending on what the daughter isotopes are. And then these can go on to cause the same process to repeat. So now we are causing a chain reaction, and now we will be getting a considerable amount of energy. If we control the chain reaction, then that's a nuclear reactor. If we let the chain reaction just go the way it's going to go, then that is a nuclear bomb. So that is your difference. Is do you control it, or do you let it just go through the process until there's no more material left? So we're going to look at those 2 different scenarios here. Anybody got a question? Okay. So this all involves something called critical mass. The idea is you have to have enough of the isotopes in an area to where most of the neutrons get used to produce more reactions. So that's what we see over here where it says critical mass. Where we have subcritical mass, we're losing a lot of the neutrons compared to how many isotopes we have decaying. We're still going to lose some, like we see here on the right, but most of them are going to collide with other isotopes, and it's going to make, so we're going to, cause our chain reaction to continue. So to have a chain reaction, we have to have a critical mass. So critical mass is required to achieve a continuing chain reaction. So now we're going to look at the bomb scenario because that's probably the easiest one. Then we'll go to the nuclear reactor. So in the first bomb that was dropped on Hiroshima towards the end of World War II, we had 2 pieces of uranium-235. So those are radioactive isotopes. And there was, as it says, a conventional explosive that caused the one piece to push into the other piece with considerable energy. So it really drove those together into a small space. And that then caused our critical mass to be achieved, which is what you're seeing over here. In the second bomb that was dropped, they tried a different sort of geometry. In this case, they were using different materials too. They were using plutonium-239, and so it was actually like a ball inside of a ball, and then you had again a conventional explosive that forced the material on the outside to then press into the material on the inside, and they again achieved critical mass and produced the explosion. So all of these devices are going to work in that same way. You'll have some pieces of an isotope that are subcritical, that cannot achieve a sustained chain reaction. But then if we press one piece into the other piece, it will go to a critical mass and have a sustained chain reaction. Now for a happier scenario, we have nuclear power generation. So what we're doing here is within the dome made of concrete and steel, quite a bit, they are going to produce steam, and that steam is then going to go outside the dome to the turbines, which will then produce electricity. And then the water circulates back in. Now that water is separated from the water that is around the core of the reactor. So there's two different waters here. There's the water that is surrounding the reactor core, which would then have, fragments of radioactive material in it. It is separated from the water that goes outside the dome where the turbine is, and but it is inside of a heat exchanger. So we are moving the heat from one water circuit to another water circuit. So there's a heat exchanger. Oops, wrong one. So the heat exchanger is where you see the blue and the red there. Because we don't want to be using the water from the reactor core in the turbine. For one thing, it will degrade the turbine. But the other reason is, for safety, we're keeping the radioactive material contained within this reactor dome. So in our next slide, we're going to see the components of a reactor. And reactors consist of fuel rods, which the fuel rod is the isotope that can then have a decay process. So that is, there's your fuel rod. And then we have control rods that can be moved up and down, and those block the neutrons. So that the neutrons that are emitted during a particular decay, if they're blocked by the control rods, they will not then go on to cause a chain reaction. So the control rods are adjusted so we get just enough of a chain reaction to heat our water to produce our electricity, but not heat it so much that we lose control and the reactor melts and things go bad. So what happened at Chernobyl was they were no longer able to move the control rods up and down. They had pulled them out. They were doing some sort of experiment, so they pulled them out more than they normally would have. And then before they could put them back in, things heated up too much, and I believe they were fused to the casing and they couldn't move them up and down. And at that point, it was over. So why are we concerned about radiation? Why does it matter? Well, if we have a source of decay particles, some sort of radiation source, and they encounter cells, it can cause damage to the DNA, which goes on to cause a cancer cell, which that cancer cell multiplies and that becomes a tumor. But the way that this is happening, if we take the DNA and we consider that we've got alternating base pairs, what will happen? Well, normally, of course, with DNA, the two strands are connected to each other through hydrogen bonding. But the hydrogen bonding is temporary. You know, it can be turned on and off. So the hydrogen bonding is temporary. So that if we need to unzip the double-stranded DNA and then either have replication or transcription, we can then allow it to come back together and preserve the integrity of the genetic material. Now, what can happen because of radiation is we can produce a permanent, oops, wrong thing, this is what I needed. We can produce a permanent link between two of the base pairs. Okay? Now, that is going to be a covalent bond. And that will be permanent. So then what will happen is during, during duplication, that will be detected as an error in the DNA, and it will try to repair it, and it'll try to cut this out. So it'll try to, during that time, remove that bad DNA and replace it with the correct DNA. But sometimes it gets it wrong. So if the repair is done incorrectly, then that is what's going to result in producing the cancer cell that we see up there. And then once that's happened, then that cancer cell can just duplicate and become a tumor. Now, the same sort of thing can happen with exposure to UV rays. And, you know, that can be from the sun. Oops. And that can be from the sun, or another way, as we know, could be the tanning bed, which I don't think too many people use that as much as they did at one time. But, you know, there was a time where everybody was hitting a tanning bed, getting their UV, and ending up with skin cancer possibly. So anyway, these are things that are controllable, and you know, you want to be taking proper precautions. Now, I got one more thing I want to say while we're on this topic, and that is some of the sunscreens, in fact, many of the sunscreens have material that itself can induce cancer. Because for it to be able to correct what's happening when ultraviolet radiation is absorbed by a cell, it has to be able to neutralize free radicals. But to be able to neutralize free radicals, it can also possibly cause free radicals, which can then induce cancer. So the message here is you should prefer sunscreens that do not use organic materials, organic compounds. Instead, have a mineral or a ionic compound. Ionic. I don't think I can spell ionic today. There we go. Ionic compounds. Such as, say, zinc oxide. Okay? That is a better option. I know it's kind of nasty, makes this white junk that you have on your skin, but on the other hand, you can find very effective sunscreens, and they're not going to cause you a problem. So anyway, just a little information you might want to share with your friends and family. So anyhow, there's your information on that. So now, talking about ionizing radiation. So we started out, we're in this chapter on nuclear chemistry. So we were, looking at gamma radiation from that, and that's the one that's going to be responsible for damaging DNA, like we just described. But this can also happen from X-rays, and it can also happen from ultraviolet, like I was talking about, or the tanning booth. Now, the thing about X-ray, though, is that's, the physician is going to make a determination in the as a cost versus benefit analysis. And they're going to determine, is it worth the possible risk that you have by using that X-ray, either diagnostic or therapeutically? Is it worth the risk or the cost for the benefit that you achieve? And so anytime that a physician is calling for some sort of treatment or diagnosis, a diagnostic X-ray, it's because they believe the benefit exceeds the possible cost. And in recent years, they've reduced the amount of X-ray that you're receiving. With dental X-rays, they have that down to just a very, very minimal amount, and they are trying to do that, in the other areas too. Now, you can see here on this chart that this is all different sorts of energy. Over on the low side here, we have things like AM radio, stuff like that. I know there are some people out there that are trying to tell you that that's gonna harm you. Well, it's really low energy, so I don't know about that. But anyway, if you look across the top here, as the wavelength gets longer, so that's what you have again with, say, AM radio, the energy is decreased. So you've got low energy, low frequency, long wavelength on the left, and you have high energy, high frequency, and short wavelengths on the right. You want to remember that relationship, okay? And I think there's 2 more slides, and I think we can get done. Oh yeah, penetrating power. Different kinds of decay particles are going to penetrate different materials. An alpha particle cannot even get through paper. Now, I am going to expect you guys to remember this stuff because other people are going to expect you to be aware of this. So, to stop alpha, all you would need is paper, but everything else would go right through. Beta, neutron, gamma. Now, these will all pass through, living organisms, but the beta particle, the high-speed electron, would be stopped by just
you would not need very much metal, just a fairly thin sheet of something. Now, if you are trying to block a neutron, it would require some water. It'll slow it down if you have enough water. That was one of the ideas for space travel, is that they would store all the water in the vehicle in the outer skin. They would have a double wall, and inside that wall would have water to block the neutrons, protect the astronauts. The gamma radiation is extremely high energy, extremely hard to stop, and the only way you're going to stop it is with a sizable thickness of lead. So please memorize this thing. Last slide. What is your typical exposure? Well, going across the ocean in an airplane, things like that, drinking water, chest x-rays, cosmic rays, radiation that's from isotopes that are naturally occurring in your body. These are all pretty low. They've got here what is the allowed public dose that you would get, typical background thing. So that's sort of this in between here. And then next we have what you would get from a whole body CT. That's why they don't do these real often, probably once a year. If you're a cancer survivor, you're going to probably be getting a whole body CT one time a year, maybe twice a year. Now this is interesting here, that the workers in nuclear power plants, they're getting a lot of radiation, even with the shielding. So I wouldn't go out and sign up for those jobs. But anyway, each their own. So anyhow, has anybody got a question? Our time has expired. Remember, we've got an exam coming up on Wednesday over those chapters. And I think that's it. If anybody needs anything, please send me an email if it's something really urgent. Also send a text message. And I believe that's it. So take care of your people. Take care of yourself. I'll see you on Wednesday. Yeah, it's in time for the summer, although we may not be able to go outside. At least, well, anyway, you guys know the story.